Morning, everyone. Thanks so much for joining us. My name is Nathan. I'm from State Audio Works in Joburg. We're a supplier and systems integrator of professional event technology solutions. And yeah, this is the first in our webinar series that we're presenting that we're calling Instruct, Insight, and Inspire. So these are the three pillars that the topics are being formed around. And yeah, this is our first one. We thought it's relevant to prepare and present some basic audio knowledge as a lot of our customers are working in churches and they haven't had professional exposure to this kind of equipment before. So I'm joined by some of my team. So yeah, let's everyone introduce themselves. So we'll start with my colleague Emtia in Namibia.
Okay, good morning, guys. My name's Emtia Smith, as Nathan said. I'm part of the State Audio Works Namibia branch. I'm involved in the installation and implementation side and the technical side regarding service and repairs as well. Personally, I've been involved in church audio since around 2000, starting from very basic up to, different levels of involvement in church audio.
Cool. And then my other colleague from Namibia, Udo.
Hey everyone, my basic knowledge is mostly in live sound and in music, but all this stuff is really great. And yeah, I'm looking forward to the session.
And then last but certainly not least, colleague in Durban, Ross.
Good morning. I've been involved in audio from about 2001 and a lot of house of worship stuff from maybe about 2007 to present day. So yeah, that's me.
Thank you, guys. Yeah, today's webinar is focused on introduction to audio. So what is it that we perceive as audio or sound? Basically, sound is energy transferred from one particle to another through a medium such as air, water, glass, whatever it is. Perceived sound is influenced by the density of the medium. Factors such as air pressure, temperature, humidity, all have an influence on the sound. If you listen to sound under the water, you'll hear that it sounds different as the medium density is different, as well as some other factors that influence it. For the same reason, in space, there's no sound because there's no air particles to transfer any energy. So in this animation, hopefully you can see it. It just shows you that there's a vibrating medium that transfers energy and the particles doesn't move themselves. They just transfer the energy going forward. So on the next slide, audio signals, as we see it, are as perceived as sine wave signals, which is a signal that increases over time to a maximum. It turns around, then proceeds to its minimum, which is then below the zero or the ground level. Or put another way, a sine wave is a sinusoid, a mathematical curve that describes a smooth periodic oscillation. If you look at the oscillating weight on the left-hand side, it goes all the way to the bottom, all the way to the top, and then again all the way to the bottom, slowly increasing and decreasing. And then the turnaround is also smooth. It's not a jagged or edgy movement. And then obviously, if we have a maximum and a minimum, that crosses the zero level from time to time. The graph on the top also shows you a sine wave that goes just up and down through the center level. And then on the right-hand side of the screen, you can see there a membrane moving air particles or transferring energy to particles, which then causes a frequency or a signal in a sinusoid wave type. Other wave signal types that we do get is square waves, more in digital, and then you've got sawtooth and triangular wave types or wave signals as well, which are not part of audio as a natural source. Sound is presented in different frequencies. So what is a frequency? The frequency of a signal can be explained as the number of times that the signal passes through that 0 point per second. This is also referred to the number of cycles per second. And generally, the human ear can hear from about 20 hertz to about 20,000 hertz or 20 kilohertz. This, however, is influenced by your age and previous exposures. Personally, I can only hear up to about 15 or 16 kilohertz, depending on a few factors on that day. Wavelength, what we see in the sound, is the distance between two of the same points. For example, the distance between the point where the wave crosses the zero level. That will give you your wavelength. The wavelength is also influenced by the medium through which it will travel. So if we look at some calculations, the wavelength can be it's presented by the Greek letter lambda, and it can be calculated as the velocity of through which the sound travels divided by the frequency. We know that the speed of sound is approximately 343 meters per second. So if you do the calculations, so 1 kilohertz sine wave has a wavelength of 34 centimeters. If you do the same math on a 100 hertz wave, you see that's got a wavelength of 3.43 meters. And then a 20 hertz signal has a wavelength of 17 meters, which is the theoretical minimum audible frequency for humans. And then 20 kilohertz, which is the maximum theoretical, or 20,000 hertz, it's got a wavelength of 1.7 centimeters. So quite a difference from 20 hertz of 17 meters to 1.7 centimeters. If we look at that in a physical representation, so the higher the frequency, the shorter the wavelength will be. There's a few examples that shows you different frequencies, which you can see that the distance between two of the same points is different for that frequency. Don't confuse wavelength or frequency for amplitude or volume level. If we look at this slide, you can see that you've got different signals of the same frequency. They cross the 0 point at exactly the same time, but they've got different levels, different amplitudes, different volumes. So on the bottom side, you can see that lower amplitude means quieter signal, softer signal. High amplitude is a louder signal. But then with a frequency, a longer wavelength is a deeper pitch. A shorter wavelength, high frequency results in a higher pitch or higher sound that we perceive. So next up, I'll play you a few samples. Hopefully you guys can all hear this. So here's 3 samples of low frequency signals. And then afterwards, we'll do some high frequency signals. So the kick drum. Keep in mind that the speakers that you are listening this to might have an influence on the sound level and sound quality that you experience. My laptop speakers doesn't do justice to any low frequency signals, but as soon as I put headphones on a decent quality, then you can hear that actually that it's quite a low signal. So a tom. And then the bass guitar. So that was just listening to it, but now we all have to do with graphic EQs and EQs, and we need to physically see what we're doing. So next I'll show you the frequency analysis of these samples. The amplitude is shown on the vertical axis, whereas the frequency is shown on the horizontal axis. You'll see that the frequencies of audio is measured in logarithmic scale, not a linear scale. And then the graph on the screen shows the theoretical range of human hearing from 20 hertz to 20,000 hertz on the right hand side here. So there's the kick drum. And you can see that's fairly low on the frequency graph on the analysis, and it covers quite a bit of frequencies. Okay, so let's go to the floor tom, same graph, same concept. In the bass guitar. And towards the end, you can see that the signal just dies off, lowers in level or the indication, and that, as we said, that refers to the volume, the amplitude of the signal. Let's look at some high frequency signals. The first will be some hi-hats from drum set. And then we'll listen to some flute sounds. Now again, let's look at the analysis of that same concept. And then for the flute. So we can see that the signal is much higher. It also covers a larger range where the audio is audible. Hopefully there wasn't too much of a delay. There might be a delay between the visual and the audio that you've heard, but hopefully you can still understand the concept and have some insight into where the frequency lies that you've been hearing. Okay, so next up is audio loudness. So audio loudness is very often incorrectly measured in wattage. But however, how loud a system is measured in SPL, sound pressure level. We'll get to wattage at a later point. So sound pressure level is the amount of air displaced by the sound source. For a given sound system, the SPL is determined by the amplitude of the audio signal. The SPL rating is measured in decibel from the inventor of the telephone, Graham Bell. And the SPL rating will always be given at a specific distance. So somebody that gives you a SPL rating without a distance of a specific speaker, that can be ambiguous and not really accurate on what we're doing. Your SPL rating or your SPL level perceiving is subject to the inverse square law. This basically just means that each time the distance from the source is doubled, your SPL signal drops by 6 dBs. So some mathematics on this. For a speaker that's emitting a sound of 110 dBs at 1 meters from the product sheet or specification sheet, at 2 meters of the same speaker, that SPL reading will be 110 minus 6, which is 104 dBs. At 4 meters, another 6 dBs less is 98 dBs, and then at 8 meters, 92 dBs. So you can see that over distance, you lose quite a bit of signal. And that becomes especially important when you're doing big PA systems, outdoor systems. You need to calculate what level of audio will be perceived by the audience area. That also is valid for indoor systems, but obviously indoor systems are normally not that large, depending on what venue you have. Sound pressure levels. So this is a table of general estimates of SPL levels that we are exposed to in general life. If you can see, so the threshold of pain, they say is 130 dBs. If you at a disco 1 meter from the speaker, that depends on what speaker it is. This graph refers to 100 dBs, a vacuum cleaner 70 dBs, your average home 50 dBs, quiet bedroom 30 dBs. So yeah, that's obviously subject to conditions around you, which vacuum cleaner, blah, blah, blah. There's also all of these, but that's just the estimate figures that they give you. Some more interesting information. So rock concerts, line range single speaker could have a SPL rating of 145 dBs at 1 meter. But that's high up, that's far from you. And the line range is designed to have even audio coverage in a certain audience area. And you're looking at probably something around 110 dBs for concert, which is being experienced at the concert, well, in the seating area, the audience area. So wattage. So what is the wattage rating all about? Amplifier wattage is the amount of energy output from the amplifier to the speaker. So this doesn't necessarily mean it resembles how loud a speaker is. The amplifier power in combination with the efficiency of the loudspeaker driver determines the SPL rating or the output rating of the speaker. As we know, the SPL rating is how loud a speaker sounds. So if you look at some information, here's 2 different speakers from different manufacturers of a similar class. Both are 10-inch powered speakers. The first one has a 300 watt amplifier rating, the second a 260 watts. So looking at these figures, we would say that the 300 watt speaker is louder. So if you have the first one, at the 300 watt on the top there, second speaker at the bottom, it says 260 watts. But if we look at the SPL rating, we can see that the The 260 watt speaker has got a maximum SPL of 121 dBs at 1 meters, whereas the 300 watt speaker only has got 116 dB rating. So this just shows you that the output audio level of the 300 watt speaker is actually less than the 260 watt speaker. And that's very important if you look at audio levels, if you're looking at buying a speaker. There's a few other factors as well that we're interested in, is the type of enclosure of the speaker, the frequency response that we look at. But if you look at volume, if you look at how loud the speaker is, you need to look at the SPL rating as well of your speaker to have an accurate insight into that. Then quickly towards the end, this is just a speaker from a manufacturer. So there we can see the sensitivity rating of the physical driver, and that is that one in combination with the amplifier and then the amount of drivers in the box. All of that you use to calculate your SPL rating. So guys, yes, thank you very much. This was the first one. There is a Q&A section which will be handled now. If there's any other questions, anything else you would like to ask us later afterwards, email us with some comments or requests. Please use the email address on the screen, which is training@stageaudioworks.com. Okay, Nathan, is there any questions that needs to be answered?
Yeah, I've been moderating them and answering them in the chat as they've been coming in. And if anyone wants to reach out with any further stuff, we'd be more than happy to answer any questions. Cool, so I guess that wraps it up then. Thanks everyone for coming.
Thank you, guys.